Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be focusing in on buffers. Now, buffers is often seen as this big, messy topic, but really what we're looking at with a buffer is any sort of solution that slows down the change of pH in a real chemical system. And so for this, in this sense, really what a buffer is it's kind of like a buffer strip on the side of a road. It gives you a little bit of extra room for adding a little bit of acid or a little bit of base. You may drift off where you want to be, but nothing terrible happens. And that's really what buffers allow solutions to do. And really, one of the big ways we can do this is look at what happens if I add strong base, such as like sodium hydroxide, to a buffered system or a system that just has water. So if I'm going to add sodium hydroxide to straight water, so let's say I add 1 mole of sodium hydroxide to 1 liter of water. So we're going to see a huge increase of the pH because we're going to go very basic very quickly because sodium hydroxide completely disassociates in water. So that 1 mole of sodium hydroxide quickly is going to decrease, and that hydroxide increases equally. So that hydroxide concentration is really going to be based on whatever the sodium hydroxide concentration was. If I add sodium hydroxide straight to water, this is a pretty good way to find the resulting concentration of hydroxide, which then I can use to go ahead and find the pOH, which in this case is 0. Yes, this is a very basic system, also known as a pH of 14. So wow, that changed quickly. Now let's go ahead and look at the same idea, but now I'm going to add a weak acid. So if I end up adding a strong base to a weak acid, this reaction goes to completion. So all that hydroxide is going to immediately react with the acid to produce the conjugate base. And it turns out that this reaction should look kind of familiar. It's essentially the reverse reaction of a base dissociation reaction. Base plus water gives us hydroxide and the conjugate acid. Well, we know that this reaction, the reverse reaction, has a very small k. That would be given by the Kb. Most of the time, this is going to be 10 to the negative third or smaller, which means that this forward reaction, yowzers, is quite big. So there's going to be very little of the hydroxide left. So we can approximate this reaction as going to completion. So if I end up adding 1 mole of sodium hydroxide to a 1 liter solution that's 2 molar in acetic acid, so a vinegar, I'm going to end up producing some acetic acid and some acetate. So we can go ahead and look at this using an ice table. I'm going to start with 2 moles of acetic acid. I'm going to add 1 mole of hydroxide. Reaction goes to completion, which means I'm going to consume both of my reactants, and this is going to happen until one of them goes to 0. Well, in this case, I have less hydroxide, so I'm going to eat up all the hydroxide, and I'm going to leave behind some acetic acid and some acetate, so about 1 mole of each. So since we're dealing with a 1 molar solution, we're assuming I didn't add any volume with that hydroxide. It means that my resulting solution will be both 1 molar in acetic acid and 1 molar in acetate. So we know how to treat the pH of this system because I produced a buffer. I can use Henderson-Hasselbalch. So I'm going to pull out Henderson-Hasselbalch. I know the pKa for acetic acid. I know that I've got both 1 molar in my acid and its conjugate base, which ta-da, means that my pH is equal to my pKa. So by adding 1 mole of sodium hydroxide, I changed the pH to about 4.75, as opposed to 14 for water. So in an unbuffered system, this reaction just shot straight to making hydroxide, which is kind of the point. But by having a weak acid present, we're able to resist the pH change of adding that hydroxide. The more acid I have, the more sodium hydroxide I can resist. I can essentially absorb it. So really what we're seeing is that when we're looking at a buffer, all we're looking at is a shock absorber. The acetic acid can, or any weak acid can absorb a strong base being added without making the pH change quite so rapidly. 4.75 versus 14 is a big difference. Similarly, it turns out buffers can also resist a pH change from a strong acid. So I can take say a nice base like acetate, add HCl, and I'll end up making the conjugate acid, acetic acid, and in this case, I'm going to release some chloride. However, we can also treat this reaction as, well, that HCl is really just ending up releasing protons, and the chloride is a spectator ion, so we'll ignore it. Well, this reaction should look fairly familiar because this is a reverse reaction of an acid dissociation reaction. And again, we know those have very small Ks, which means that this reaction going in reverse is going to be very big K. It's always pretty much going to go to completion. And the products will just be based on the limiting reagent, whether I have less base or less acid. So as long as I have some weak base present, I can go ahead and absorb up any of that strong acid. And this will essentially slow the pH change. The more base I have, more I can nom the acid. And again, slow down any changes by keeping it in that Henderson-Hasselbalch region of having both the base and its conjugate acid. So this is really kind of the big feature of looking at buffers is we can go ahead and have a buffer by having both weak acid and weak base. That way I can go ahead and resist any change by adding an acid or a base. And it will keep that pH relatively close to the pKa as long as the amounts of acid and base present at any given time are pretty similar. So really what we're doing is we're either absorbing excess hydronium or excess hydroxide, and again, converting that excess just by shifting the reaction forwards and backwards. So relatively minor changes to the ratio instead of big changes to the available protons or hydroxide present. So if we want to construct a buffer to help resist these changes, we can do it in three key ways. First, what we saw last time, we can mix together a weak acid base pair. So again, things like acetic acid and acetate, ammonia, ammonium, hydrofluoric acid, fluoride, any number of combinations, each with a slightly different pKa. Alternatively, I can take a weak base and add a strong acid, producing a weak acid base mixture. Conversely, I can take a strong weak acid and add a strong base, making a weak acid base mixture. So these are going to be the three major ways that's very typical to make a buffer. Next time, we're going to see what it takes to essentially make a buffer not work as we talk about buffer capacity. Until then, take care.